Download this code from codegive.com, link in the description below. OK, let's dive deep into graph identification and privacy in social networks, combining theory with practical code examples. This will be a comprehensive exploration. Introduction, the landscape of social network privacy. Social networks have become integral to modern life, connecting billions of individuals. However, the interconnected nature of these platforms presents significant privacy challenges. A user's connections, activities, and shared content form a complex graph that can reveal sensitive information, even if the user tries to be cautious. Two key privacy issues we'll address here are: 1. Graph identification. Anonymity attacks. Can an attacker identify a specific user within a seemingly anonymized or perturbed social network graph? This is especially concerning in scenarios where the released data is intended for research or public benefit but inadvertently compromises user privacy. 2. Inference attacks. Can an attacker infer private attributes of a user, example political views, health conditions, based on their connections, activities, or the characteristics of their neighbors in the graph? 2. Understanding social network graphs. A social network graph is a representation of relationships between individuals. Mathematically, it's defined as *G equals V E *V*, a set of nodes, vertices, representing individuals or entities. *E*, a set of edges, representing relationships or connections between nodes. Edges can be directed, example following on Twitter, or indirect, example friendship on Facebook. Key graph concepts: degree, the number of edges connected to a node. Neighbor, a node directly connected to a given node. Adjacency matrix, a matrix representation of the graph, where Aij equals 1 if there's an edge between node I and node j, and 0 otherwise. Path, a sequence of nodes connected by edges. Shortest path, the path with the fewest edges between two nodes. Clustering coefficient, measures the degree to which nodes in a graph tend to cluster together. For a node, it's the ratio of actual connections between its neighbors to the maximum possible connections. Centrality measures quantify the importance of a node within the graph. Common measures include degree centrality, the node's degree, number of connections. Betweenness centrality, the number of shortest paths that pass through the node. Closeness centrality, the average distance, shortest path length, from the node to all other nodes in the graph. Eigenvector centrality, measures a node's influence based on the influence of its neighbors. Nodes connected to highly influential nodes are themselves more influential. 3. Graph identification attacks. The goal of a graph identification attack is to re-identify a node in a perturbed or anonymized graph based on information about the node's connections in the original graph. This becomes a privacy risk when the attacker has external knowledge or auxiliary information about the user. Attack techniques: 1. Node re-identification based on structure. Degree-based attacks. The simplest approach: if the attacker knows the degree of a target node in the original graph, they can search for nodes with the same degree in the anonymized graph. This is often insufficient on its own due to the high probability of multiple nodes having the same degree. However, degree can be combined with other properties to refine the search. Neighborhood-based attacks. Exploits the structural information of a node's neighbors. The attacker might know the degrees of the target node's neighbors in the original graph and look for nodes in the anonymized graph with similar neighbor degree distributions. Subgraph matching. Asterisk the attacker tries to find a subgraph around the target node in the anonymized graph that matches a known subgraph from the original graph. The larger and more unique the subgraph, the more successful this approach is. Asterisk graph alignment / graph isomorphism asterisk. Asterisk the attacker tries to find a mapping between the nodes of the anonymized graph and the original graph that preserves the connections, edges. This is a complex problem, NP hard in general, but efficient algorithms exist for smaller graphs. 2. Link re-identification asterisk. Asterisk if an attacker knows the existence of a link between two specific individuals, they can search the anonymized graph to identify the corresponding nodes. This is especially problematic if the link is sensitive, example a connection to a medical professional. B code example, degree-based re-identification, Python with network X. Explanation of the code asterisk. 1. Create _sample graph, asterisk generates a random graph with a specified number of nodes and a probability of connection between any two nodes. You can adjust the n_nodes and connection probability to control the graph size and density. 2. Anonymize graph, asterisk in this simplified example, it just returns the graph as is. In a real-world scenario, this function would perform anonymization techniques, discussed later. The purpose here is to isolate the re-identification attack. 3. Degree_based re-identification, asterisk this function takes the original graph, the anonymized graph, and the degree of the target node as input. It iterates through the nodes in the anonymized graph and identifies those with the same degree as the target node. These nodes are considered potential re-identifications. 4. Degree_based re-identification with neighbors, asterisk this function is an advanced version of the previous one, which takes into account the degree of the neighbors of a given node as well. It calculates the number of common neighbors with the same degree as the original target node and defines a threshold that must be met to qualify as a potential re-identification candidate. Important notes asterisk. Asterisk this is a very basic example. Real-world social networks are much larger and more complex. Asterisk degree-based attacks are often insufficient on their own. The effectiveness of the attack depends heavily on the graph structure and the uniqueness of the target node's degree. Asterisk more sophisticated attacks exploit more complex graph features and require more advanced algorithms. Asterisk the neighbor_degree_ threshold is an important parameter that needs to be tuned. 4. Privacy-preserving techniques for social networks. Several techniques are used to protect the privacy of users in social networks while still allowing for data analysis and research. These techniques aim to reduce the risk of re-identification and attribute inference. A. Anonymization techniques asterisk. 1. K-anonymity asterisk. Asterisk the goal of K-anonymity is to ensure that each record in the anonymized dataset is indistinguishable from at least K1 other records based on a set of quasi-identifiers, attributes that can be linked to external data to identify individuals. Asterisk in the context of graphs, K-anonymity can be applied to node properties, example attributes associated with each node. It doesn't directly address the graph structure. 2. L-diversity asterisk. Asterisk an extension of K-anonymity that addresses the limitations of K-anonymity when dealing with sensitive attributes. It ensures that each equivalence class, group of K-indistinguishable records, has at least L well-represented values for the sensitive attribute. Asterisk in graphs, this could mean ensuring that the sensitive attribute, example membership in a particular group, is diverse within each K-anonymized group of nodes. 3. T-closeness asterisk. Asterisk another extension of K-anonymity, addressing limitations of L-diversity. it requires that the distribution of the sensitive attribute in each equivalence class is close to the distribution of the sensitive attribute in the entire dataset. Closeness is typically measured using metrics like Earth mover's distance, EMD. For graph modification techniques asterisk edge perturbation adding or deleting edges randomly to the graph. This changes the graph structure, making it harder to re-identify nodes based on their connections. Node generalization aggregating nodes into supernodes, example grouping individuals into larger geographic regions or age ranges. This reduces the granularity of the data. Node suppression removing nodes, and their connections, from the graph. This can be used for nodes that are considered particularly vulnerable or have sensitive information. Differential privacy differential privacy, DP, is a rigorous mathematical framework for privacy protection. It guarantees that the presence or absence of any single individual's data in the dataset will not significantly affect the outcome of a query or analysis. DP is achieved by adding carefully calibrated noise to the data or query results. The amount of noise is controlled by a privacy parameter, epsilon. A smaller epsilon indicates stronger privacy protection but may also reduce the accuracy of the results. In graph analysis, DP can be applied to various tasks, such as releasing degree distributions, calculating centrality measures, performing community detection. DP is a powerful technique, but it requires careful implementation and consideration of the specific data and analysis being performed. B-code example, edge perturbation, Python with network X. Explanation one edge perturbation, takes the original graph and a perturbation rate as input. It iterates through all possible edges and adds or deletes them with the specified probability. Two important considerations The perturbation rate controls the level of privacy protection. Higher rates provide stronger privacy but also introduce more distortion into the graph. Adding and deleting edges affects the graph's properties, such as degree distribution, clustering coefficient, and centrality measures. It's important to choose a perturbation rate that balances privacy with data utility. Edge perturbation can be combined with other anonymization techniques to achieve stronger privacy guarantees. See code example, applying differential privacy, simplified. Applying true differential privacy is a more complex task because it requires analyzing the sensitivity of the queries and carefully calibrating the noise. Here's a simplified example to illustrate the concept of adding noise. This code does not guarantee differential privacy without proper sensitivity analysis and calibration. Important notes on differential privacy sensitivity the sensitivity of a query is the maximum amount that the query's result can change if a single individual's data is added or removed from the dataset. Accurate sensitivity analysis is crucial for calibrating the noise. The sensitivity calculation is complex and depends on the specific query you're running on the graph. Noise distribution The Laplace distribution is commonly used for adding noise in DP. The scale parameter of the Laplace distribution, which is 1/epsilon in the simplified example, needs to be carefully calculated based on the sensitivity. Privacy budget When performing multiple queries on the same dataset, you need to manage the privacy budget, epsilon. Each query spends some of the budget. Sophisticated techniques like composition theorems and advanced composition theorems are used to track the privacy budget and ensure that the overall privacy guarantee is maintained. There is also the notion of delta which contributes to the budget. Libraries like diffpriblib in Python provide tools for implementing DP in a more robust and accurate way. Using these libraries is highly recommended. Inference attacks. Inference attacks attempt to infer private attributes of a user based on their connections, activities, or the characteristics of their neighbors in the graph. Examples of inference attacks: 1. Homophily-based inference. Homophily is the tendency of individuals to associate with others who are similar to them. If an attacker knows that a user is connected to a group of people with a certain characteristic, example political affiliation, health condition, they might infer that the user also shares that characteristic. 2. Structural inference. Exploiting structural properties of the graph to infer attributes. For example, if a user is a bridge between two distinct communities, the attacker might infer that the user has knowledge or connections related to both communities. 3. Collective inference. Iteratively inferring attributes of multiple users based on their connections. The attacker might start with a small set of users with known attributes and then use those attributes to infer the attributes of their neighbors, and so on. Code example: homophily-based inference, simplified. Explanation. 1. Create _graph with _attributes. Creates a graph where each node has a binary attribute, 0 or 1. Nodes with the same attribute are more likely to be connected. 2. Homophily-based inference. Attempts to infer the attribute of a target node based on the attributes of its neighbors. It randomly selects a subset of the target node's neighbors whose attributes are known and infers the target node's attribute based on the majority. See defenses against inference attacks. 1. Attribute suppression. Hiding or generalizing sensitive attributes. 2. Privacy-preserving link prediction. Modifying edge structure so that it is harder to determine the real links. 3. Homophily reduction. Modifying the graph structure to reduce the correlation between node attributes and connections. 6. Advanced topics and considerations. Dynamic social networks. Real-world social networks are constantly evolving. Nodes join and leave, edges are created and deleted, and node attributes change over time. Privacy-preserving techniques for dynamic graphs are more challenging than for static graphs. Multi-relational graphs. Social networks often have multiple types of relationships, example friendship, family, co-worker. Multi-relational graphs require more sophisticated privacy-preserving techniques that take into account the different types of relationships. Federated learning on graphs. A decentralized learning approach where models are trained on data distributed across multiple devices or organizations without sharing the raw data. This is a promising approach for privacy-preserving graph analysis. Adversarial machine learning for graphs. Developing machine learning models that are robust against adversarial attacks, including attacks that aim to infer private information. 7. Ethical considerations. Data minimization. Only collect and store the data that is absolutely necessary. Transparency. Be transparent about how data is being collected, used, and protected. User control. Give users control over their data and allow them to opt out of data collection or anonymization. Fairness. Ensure that privacy-preserving techniques do not disproportionately harm certain groups of users. 8. Conclusion. Graph identification and inference attacks pose significant privacy challenges in social networks. A combination of anonymization techniques, differential privacy, and careful attention to ethical considerations is necessary to protect user privacy while still enabling valuable data analysis. The specific techniques used will depend on the specific data, analysis goals, and privacy requirements. This is an active area of research, and new privacy-preserving techniques are constantly being developed.